NVIDIA in the Valley. NVIDIA investors have been in the valley before. Crypto isn't so much a valley as it is a cliff. Ethereum successfully transitioned to a proof-of-stake model, rendering entire mining operations, built with thousands of NVIDIA GPUs, worthless overnight, given that Bitcoin, the other major crypto network to use proof-of-work, is almost exclusively mined on custom-designed chips. All of those old GPUs are flooding the second-hand market. Now Christian had not gone far in this valley of humiliation before he was severely tested, for he noticed a very foul fiend coming over the field to meet him. His name was Apollyon, Destroyer. What was striking about NVIDIA's GTC keynote last week was the extent to which this allegory seems to fit NVIDIA's ambitions. The company is setting off on what appears to be a fairly solitary journey to define the future of gaming, and it's not clear when or if the rest of the industry will come along. Moreover, the company is pursuing a similarly audacious strategy in the data center and with its metaverse ambitions as well. In all three cases the company is pursuing heights even greater than those achieved over the last 2 years, but the path is surprisingly uncertain. The presentation of 3D games has long depended on a series of hacks, particularly in terms of lighting. Finally, light is applied based on the position of a predetermined light source, with a shadow map on top of that. Ray tracing handles light completely differently. Instead of starting with a predetermined light source and applying light and shadow maps, ray tracing starts with your eye, or more precisely, the camera through which you are viewing the scene. It then traces the line of sight to every pixel on the screen, bounces it off that pixel, based on what type of object it represents, and continues following that ray until it either hits a light source, and thus computes the lighting, or discards it. I took the following screenshot pairs in Square Enix's Shadow of the Tomb Raider for PC, which supports ray-traced shadows on NVIDIA GeForce RTX graphics cards. That is why NVIDIA introduced dedicated ray tracing hardware in its GeForce 2000 series line of cards, which were thus christened RTX, which came out in 2018. AMD went a different direction, adding ray tracing capabilities to its core shader units, which also handle rasterization. This is slower than NVIDIA's pure hardware solution, but it works, and, importantly, since AMD makes graphics cards for the PS5 and Xbox, it means that ray tracing support is now industry-wide. For now, though NVIDIA is already using AI to render images, the company also announced version 3 of its deep learning supersampling (DLSS) technology, which predicts and pre-renders frames, meaning they don't have to be computed at all. Previous versions of DLSS predicted and pre-rendered individual pixels. These new approaches, matched with dedicated cores on NVIDIA's GPUs, make NVIDIA very well placed for an entirely new paradigm in not just gaming but immersive 3D experiences generally, like a metaverse. NVIDIA's new GPUs are big chips. The top-of-the-line AD102, sold as the RTX 4090, is a fully integrated system on a chip that measures 608.4 square millimeters on TSMC's N4 process, won the top-of-the-line Navi 31 chip in AMD's upcoming RDNA 3 graphics line. In comparison, is a chiplet design with a 308 square millimeters graphics chip on TSMC's N5 process, 2 plus 637.5 square millimeters memory chips on TSMC's N6 process. 3 In short, NVIDIA's chip is much larger, which means much more expensive, and it's on a slightly more modern process, which likely costs more. NVIDIA first came to prominence with the Riva and TNT line of video cards that were hard-coded to accelerate 3D libraries like Microsoft's Direct3D. The GeForce line, though, was fully programmable via a type of computer program called a shader. I explained more about shaders in this daily update. More importantly, shaders didn't necessarily need to render graphics. Any sort of software, ideally programs with simple calculations that could be run in parallel, could be programmed as shaders. The trick was figuring out how to write them, which is where CUDA came in. This is why NVIDIA transformed itself from a modular component maker to an integrated maker of hardware and software. The former were its video cards, and the latter was a platform called CUDA. The CUDA platform allows programmers to access the parallel processing power of NVIDIA's video cards via a wide number of languages, without needing to understand how to program graphics. Anything that's programmable, anything that could do more than one thing just by definition carries a burden that is not necessary for any particular one task, and so the question is, when do we do it? Well, there was also an inspiration at the time that everything looks like OpenGL Flight Simulator. Everything was blurry textures and trilinear mipmapped, and there was no life to anything, and we felt that if you didn't bring life to the medium and you didn't allow the artist to be able to create different games in different genres and tell different stories, eventually the medium would cease to exist. At the same time, we also were driven to not go out of business someday because it would be commoditized. This is the course that all of the biggest companies will likely follow. They don't need an NVIDIA system, they need a chip that works in their system for their needs. That is why NVIDIA is so invested in the democratization of AI and accelerated computing. The long-term key to scale will be in building systems for everyone but the largest players. In the interview last spring, I asked Huang if NVIDIA would ever build a cloud service. What is worth considering, though, is that the number one reason why NVIDIA customers, both in the consumer market and the enterprise one, get frustrated with the company is price. NVIDIA GPUs are expensive, and the company's margins, other than the last couple of quarters, are very high. Pricing power in NVIDIA's case, though, is directly downstream from NVIDIA's own innovations, both in terms of sheer performance in established workloads, and also in its investment in the CUDA ecosystem, creating the tools for entirely new ones.